Hello, I'm David Patterson, retired research scientist. Part 7. I want to apologise up front for the length of all these talks. Part 1, 2, 3 introduced the theory of ordinal numbers, of non-standard analysis, and of limits. Parts 4, 5 and 6 were applications in quantum mechanics, in computer science, in divergent series. In part 7, you should just treat this as a light-hearted interlude, so no need to panic. I'm not assuming any knowledge of mathematics whatever. The only thing with a serious intent in this is the paradox of Hilbert's hotel, and that's not serious because it's in any way difficult to resolve, but it's serious because it's quoted so often over and over again. Take-home messages from part 1 for this talk. When I talk ordinal infinity, I mean ordinal infinity from non-standard analysis. Ordinal numbers are literally just numbers sorted in order of size. So, first, second, third, fourth, fifth, as opposed to cardinal numbers 1, 2, 3, 4, 5. Feature of the ordinal infinity I'm using here is written as omega, and omega is not equal to omega plus 1, and omega plus 1 is equal to 1 plus omega. Infinity times 0 equals 0. It's very useful. Infinity is infamous for creating paradoxes, but let's start with paradoxes that don't rely on infinity. For example, the paradox 1 times 0 equals 0 and 2 times 0 equals 0, so 1 equals 2. It's a paradox that doesn't involve infinity. Another famous paradox that doesn't rely on infinity is Russell's Barber paradox. In a small town, there is a barber who shaves everyone who doesn't shave himself. Who shaves the barber? This contains negative self-reference, which is similar to saying this statement is false. Is that statement true or false? Because if it's true, then it's false, and if it's false, then it's true. Paradox 1. There is an excellent collection of more than 20 paradoxes involving infinity in the book by Graham Oppy, 2006, Philosophical Perspectives on Infinity. Most of these rely on the statement infinity equals infinity plus 1. But if infinity is not equal to infinity plus 1, the paradoxes vanish. A paradox that I particularly like is called deafening peals. A church bell is so loud that anyone standing in the belfry is instantly deafened. The bell is rung an infinite number of times before noon. A person is unlucky enough to be standing in the belfry during the sequence of rings. He is not deafened by the ring at noon because he is already deaf before that, nor by the rings before that noon ring. So he cannot be deafened by any of the rings, so he must survive the whole experience with his hearing intact. Leaving aside the physical impossibility, the simple solution to this paradox is to note that the infinite number omega is the number of natural numbers. So he is deafened by ring number omega, and his hearing does not survive intact. It doesn't matter that the natural numbers have no upper limit, because omega is an upper limit. Zeno's paradox of the arrow. In this paradox, an arrow must jump from one point in space to another point in space. It can't jump instantaneously because then its speed would be infinite. So it must stop at each point in space for a time period. The arrow is not moving during that time period, so it must have a speed of 0. In other words, the arrow cannot move at all. In Newtonian mechanics, we have infinitesimals of different sizes. An arrow moves an infinitesimal distance in space, dx, in an infinitesimal interval of time, dt. So it never stops at a point in space and can move. Its velocity is the ratio of the two infinitesimals. On the other hand, if space is quantized, we can even claim that Heisenberg's uncertainty principle is a direct consequence of Zeno's paradox of the arrow. Paradox 4. Zeno's Achilles and the tortoise. A more difficult version of this is as follows. If Zeno takes a step which is half a kilometre in half a minute, quarter of a kilometre in a quarter of a minute, eighth of a kilometre in an eighth of a minute, how many steps does Achilles need to reach the end of the race 2 kilometres away? The answer can't be infinity, because after an infinite number of steps, Achilles is still only 1 kilometre away from the start line. He's still 1 kilometre short of the finish line. To solve this paradox requires a number larger than infinity. If your system of infinite numbers doesn't have infinities of different sizes, then they can't solve this paradox. Paradox 5. I really like this one because it's just elementary algebra. Without the use of infinitesimals, we end up with 2 equals 1. With the use of an infinitesimal, we end up with a plus b equals b plus a, which is perfectly reasonable. Paradox 6 is Hilbert's hotel. This has been quoted more times than I can remember, and only a single interpretation has been given in each case. In order to accommodate a new guest into a room already full, he asks the guest in room 1 to move into room 2 to room 3, etc. The new guest moves into room 1. Therefore, infinity equals infinity plus 1. But there are many alternative ways to interpret this. The first one, I want to draw your attention to the difference between an ordinal and a cardinal number. We can say 1 is third and first is 3. We can equate an ordinal number to a cardinal number that's got a different value. But we can't say 1 equals 2, and we can't say first equals second, unless we also say second equals first. So in this case, what Hilbert is trying to do, if we treat these as sorted numbers, ordinal numbers, Hilbert isn't trying to move a guest from room 1 to room 2. He's trying to move room 1 itself into room 2, which he can't do, because the ordinal numbers are the rooms. And there are various other alternatives to this. The fourth one here is Cantor's. When he introduced his Cantor's ordinal infinity in the first place, he said, a new guest can move into the first room because the others can shift out of the way. But a new guest can't move into the last room because there is no last room. So first room, 1 plus infinity equals infinity, but infinity is not equal to infinity plus 1 because a guest can't move into the last room. And this gives a system of numbers which is called non-commutative. It's not a mathematical field and it's not particularly useful, but it has been studied in detail by several mathematicians. Now we're getting on to some of the more difficult paradoxes, and for that I need to jump back to part 3 of this talk. The surreal numbers of Conway. Each number can be written A bar B, where A and B are sets, a set being just a collection of numbers. Every element in A, an element in A is just a number. So every number in A is smaller than every number in B. And this, with the arbitrary symbol bar between them, tells us that this new number is between every number in A and every number in B. And since every number in A is less than every number in B, there must be a number in the middle between the two of them. If A and B are both empty, then the result is the number 0. A hyperreal number is the limit of an infinite increasing or decreasing sequence. A sequence here is just numbers in order. So 1, 2, 3, 4, 5 are numbers in order. There are extra constraints imposed, called a filter, to stop the difference between two sequences being anything other than in the same direction, by disposing of unwanted terms in the sequence. Paradox 7. Is infinity odd or even? You'd think, well, obviously it can't be odd, can't be even, can't be both, can't be neither. And in fact, that's correct. Infinity is not specifically odd, specifically even, specifically both, or specifically neither. To solve instead, you are free to choose whether any particular infinite number is odd or even, but once chosen, the answer remains fixed for the remainder of the calculation. So if we choose infinity to be even, then infinity plus 1 must be the opposite. The set of all sets. This is a very famous paradox. Suppose there is a set that is the set of all sets. Now that seems pretty crazy, doesn't it? Can't possibly exist. And set theory says it can't exist. The laws of set theory prohibit it specifically. But the set of all numbers does exist. The set of all natural numbers does exist. The set of all integers does exist. So the set of all sets is not such a crazy idea. Since we're talking about numbers, a set is just a collection of numbers. So an infinite sequence such as 0 is the limit of 0, 0, 0, 0, 0, 0, 0, etc. is a set that contains itself. On the surreal numbers by Conway, the number x can't be a member of either of the sets A or B, so no set can contain itself, and the statement, the set of all surreal numbers, is free from paradox. On the hyperreal numbers, we can define the number 0 to be itself, to be based on itself. Does this mean that the set of all hyperreal numbers cannot exist because of the paradox? The answer is no, because although the sequence, that what sequence is equal to 0, it does not specifically define 0. There are other ways to define 0. Every hyperreal number is defined in a way that doesn't involve self-reference, and so the set of all hyperreal numbers is free from contradiction. And that's all I've got for you. Here are the take-home messages. Famous paradox of Hilbert's hotel has at least 5 alternative interpretations. Paradoxes that don't rely on infinity can be extended to include infinity, but altogether it looks as if the use of ordinal infinity for non-standard analysis can resolve without conflict every paradox that relies on infinity and doesn't lead to any new paradoxes. And this slide is just if you want to read some more of what I've written or look at videos from the previous parts of this talk. Bye for now.